Okay, welcome back. My name is Wayne Gralick, and we'll be doing sort of the second little mini lecture on surface mount. This is going to be a shorter version of my talk that I gave last November at the Homebrew Robotics Club on surface mount technology. So that took about an hour and 15 minutes. I'm going to try and squeeze this down to about 15 minutes pretty quickly. Okay. So what is surface mount technology? It's basically robots assembling electronics. It's a sort of broad category of stuff. There's something called surface mounted components, which are the little packages here, little black ones. Oh, that thing keeps falling. Okay. You have surface mount equipment, which we call pick and place machines. They pick up the components from carriers and drop them on the board. And then you have things that do the reflow ovens that cook them up and melt the solder and stuff like that. The reason for doing surface mount technology is because it's smaller, faster, cheaper. Borrowed that from NASA. It's also higher quality. Okay. So those are its advantages. The disadvantages are it's harder to see. It can take longer to prototype. It really depends upon your skill level. There are some people who are way better at surface mount than I am, and they're faster than I can do through hole. But people like me, no, surface mount really is probably about 5-6 times longer for me to do than through hole. And you definitely need more skill. Okay, so I can teach somebody to do through-hole soldering in half an hour. Surface mount, I think you're looking at a learning curve that's measured in hours, tens of hours, to get up to a good skill level. The people who are really good at it, they can put down a fine pitch part, and they literally take their soldering iron and just drag it across the pins, and every pin is perfectly soldered, and they do that in about 5-10 seconds. Impressive as all get out. I can't do that. I talked about a bunch of this in the back. What's your process? You design your board. Okay, you get it manufactured, and then you either individually solder each component, or you do a solder paste process. Solder pasting is done with a stencil. Here's a stencil. This is made out of Kapton, which is a very robust plastic. It's got really small holes in it. I don't know if you can see the holes behind through the thing. Some people will also cut these out of Mylar. Okay, and the professionals use stainless steel. And they put them in a very rigid frame. You can pass some of those around, sure. Yeah, I have like 8 or 9 of them in there. And so the solder paste process is you lay this down on top of the board, and then you take something called solder paste, which is little balls of solder in flux, and you squeegee them on here, and then you just lift it, you peel this back, and it leaves little dabs of solder paste all over the place. And you can still, after that, you can manually place your parts, which is what I do now. And then if you've got the right equipment, you can have a machine to place them. That's called a pick and place machine. By the way, I'm actually working on getting an inexpensive pick and place machine going, because I'm so bad at the tweezer time, is what we call it. It goes into a reflow oven, which is basically we heat it up to approximately 200 degrees centigrade. That will melt the solder. Depends upon which kind of solder you use. They have different melting points. We'll talk about that later. After you've done that, you test the board, and usually you find a whole bunch of mistakes. And so for the mistakes, you break out your X-Acto knife, you cut traces, you scrape off solder mask, you attach wires, and you fix up your board. and then you get to do it again. And that's why all of our boards have the infamous revision letter on it. Okay, so this is revision B. Okay, I'll be sending a revision C in the next few weeks. That's just kind of the process. So you never get it right in revision A, and you rarely get it right in revision B. And I've been up to, some of my boards have gotten as far as revision G. Now that wasn't all mistakes. That's sometimes you're going like, I need to add this feature. So anyhow, that's kind of the process. Is you iterate until you're happy with your product. Now the kinds of parts that we have for surface mount components are, they tend to be all the resistors and capacitors are these little square things. You can't even see them here. I mean, I could take this thing within 10 inches of the camera. Maybe we'll be able to, but it probably is going to lose focus.
Yeah.
Okay, anyhow, that's as close as I can. You can't even see them. Okay. They get as small as 4/1000ths of an inch by 2/1000ths of an inch. And, I can't even see them. Okay. Now on these boards you have some slightly larger things like these are diodes. So if I brought them close, you could see it. The really big black thing is the microcontroller. Okay. So we have the surface mount passives, which are 2 lead devices. You have the 3 to 6 lead devices, which are usually in something called a SOT, S-O-T. It stands for small outline transistor. I have 3 of them on this board, here, and there. You can't see them. So, we will sometimes put dual inline packages on here, but the moral equivalent is called SOIC, so for small outline integrated circuit. And so I have some of those on here. Again, my finger's right near one. And then we get to the big packages, which are the quad packages. So those are called quad FP, QFP, quad flat pack. And then the really big stuff is the ball grid array. I've never touched them. And then there's something called bare chip. Okay, I think that's COB. It stands for chip on board, I believe. And
CSP or chip scale package.
Chip scale package. And I've never done that. Apparently it's not as bad as you might think. But I'm sure you've all seen it. When you get one of those boards and it's got that little dab of epoxy on it, they have directly soldered that chip to the board, and then to protect the chip, they've covered it with a dab of epoxy. Okay, so that's how that's done. So it's not as bad as everybody might think. It's kind of like ball grid array, but a little bit. Okay, so yeah, I don't want to spend too much time on the parts. Tools. Okay, you don't do printed circuit boards with tape on clear Mylar anymore. It's all done electronically with ECAD tools. There's the professional tools like LTM and OrCAD. Does anybody here, anybody ever used one of those? Once, okay. Which one?
OrCAD.
OrCAD, okay. I don't even know who owns OrCAD these days. Is it Mentor? No, don't know, okay.
Decade plus.
Yeah, right. So we tend to use the freer stuff, okay. The free stuff is, the most popular one in the hobbyist space is Eagle. It's proprietary software. They give away, I don't want to call it a crippleware, but that's kind of the word that's used out there. It's where they restricted features on it. They've been very generous. I think it's a very nice package. Their goal is to get you hooked on it, and then when you need some more features, then you start paying. I think it's a reasonable business model. Okay. I use KiCad. It's completely 100% free, 100% open source. And oh yes, it can read in Eagle files. So that's kind of why I do Eagle. The one that preceded KiCad that was free is called the GNU Electronic Design Automation Suite. GITA is the way I pronounce it. I don't know how other people pronounce it. Believe it or not, I actually use one of the tools from the GITA test suite because I think it's better than KiCad's. And then for people who are Windows, there's one that seems pretty workable called Free PCB. And I actually get my footprints from Free PCB, and I've converted them over to KiCad. That's how I do. So you'll notice that I sort of pick and choose from what's available out there.
So KiCad does not work on Windows?
Questions. KiCad does work on Windows, to answer the question. It works on Mac OS as well. Yeah, so, okay. So I'm trying to keep this to within a reasonable amount of time. Okay. The process of schematic capture, I talked about this, footprint selection, board layout, and then Gerber generation. Gerbers are the descriptions that are sent out to the manufacturers to build the printed circuit boards. The history, briefly, is that Gerber created something called a photoplotter, which was the original technology that they used to make these things. Nobody's used a photoplotter in decades. Okay. When you're doing your boards, you will almost always have to create your own footprints because you won't be able to find one that's pre-made for you. So part of the process of doing a board is discovering that the part that you have selected for your board, you can't find a footprint. So we're going to have to teach you how to make a footprint for it. Okay. A footprint is technically called, the landings for the part, and it's where the leads are supposed to land on the copper that you will solder. Okay. I tend to use a naming convention for my footprints called IPC for 7351. Okay. I'm not sure what IPC stands for. The PC is printed circuit. I think I is for international. I can't give you a solid one on that. Okay. I've talked mostly about the manufacturing in the previous one. We send them out. Okay. I should mention, I get 10 boards that are 10 centimeters by 10 centimeters for $25 from Seed Studio. Okay, it is just absolutely incredible. Okay, I used to pay $50 for a board not much larger than this from Bulgaria, Olenex, and I thought I was getting a deal, and now it's just completely an order of magnitude cheaper, and the quality seems to be very good these days. These are 100% tested boards. It's just amazing. And the other thing is you are allowed to put smaller projects, put multiple projects on this board. So I actually have a total of 6 projects on this 10 centimeter by 10 centimeter board. At home I have a metal shear that I use to cut the boards. And we'll talk about board cutting, because it turns out you don't really want to breathe fiberglass dust. Okay. Now we're going to have to talk about the tools. I'm not going to talk about them in detail here, but you're going to need a good soldering iron. Temperature controlled, fine tip, okay? You're going to need it. You're also going to want to get some good solder, okay? And we're in the United States. We do not have to use solder that is lead-free. And I recommend that we do not go with lead-free solder. It's harder to work with, okay? The leaded solders you use here, it's really not that dangerous to the environment to use leaded solder in the small quantities that we're going to use it for. For mass production, go lead-free. It's the right thing to do. But for the prototyping that we do, stick with the lead. It's easier. Okay. We're going to need Rework Stations. Okay, that's basically a hot air gun that's temperature controlled. I think David has brought his in. Okay. So we're going to need that, and that's how you fix mistakes. Some people actually solder with their hot air gun. Okay, they just put the board down there and they just blow hot air on it, and they use that to melt the solder. So that's another soldering thing. There's the vision issue. In general, the younger you are, the better your eyesight, and so so a lot of people who've got good eyesight can do the surface mount, they just eyeball it. I cannot, so I have to have a microscope. So we'll talk about microscopes if you want to you know, where you get them, you know, what to get if you want to get your own. There seems to be a pretty nice microscope out here in the electronics section, so we'll go with that. And then comes the toasting part, you know, reflow. A lot of people will use an electric skillet. Okay, I've never done that, but it's a popular way of doing it. I use a toaster oven, and there's this Chinese reflow oven that more and more people are ordering, and we may be getting one here in the lab. You know, a friend of mine has one on order, and it should be showing up in the next week or so. So hopefully we'll be able to give it a try. And after you've baked them, there is a cleaning step where you're supposed to get all the gunky solder flux off. I use isopropyl alcohol on a toothbrush. Some people use an ultrasonic cleaner. Yeah, there it is, the alcohol. Okay, and I said we do cutting. Okay, I've talked a bit about the solder paste. We're going to go into the issues of solder paste. There are a lot more. It used to be you had to refrigerate them, warm them up carefully, and be very careful with them. They've got the formulations a lot better now, so you can be. It's a lot easier to work with solder paste. And then after you've soldered this stuff, mistakes happen. So for example, on these fine pitch parts, you get things called solder bridges, where the solder gap bridges between two pins. So we'll show you how to remove a solder bridge, okay, using something called solder wick and flux. We'll also teach you how to sort of pull on all the pins to make sure that they're properly soldered, because it can look soldered, but your project isn't working because there's a little air gap between the pin and the thing. So we want you to test to make sure that every pin is properly soldered. Okay. Now, when it comes to stencils, I currently send my stencils out to be made, but a friend of mine has successfully laser cut some stencils on his laser cutter. We haven't done a fine pitch part yet, but we're going to give it a try. And who knows, maybe we can be making our own and not have to send out. Okay. And then I want to wrap up with microcontrollers. I talked a little bit about that and the other thing. The key thing about microcontrollers is the design for debuggability. So that means adding test points where you think you're going to want to look at signals. It can be a little hard to hold that probe on that pin that you forgot to leave a test point for, so you definitely want to leave test points lying around on your board. You want to put an LED or 2 or 4 or 8 on the board so that you have a way of sending information out by just saying, I got here, and you can light an LED. Probably the most important thing is to put some sort of Jtag connector on the part. This is the Jtag connector I use. It can also do serial debugging. It's kind of large. You get away with it because it's almost free, because this connector on my boards is already big. Now, most people use a smaller connector than this when they do Jtag, providing they don't have some trick like hiding it the way I did it. Okay, because I've hidden this connector basically right on the edge there. So we definitely want to do Jtag. And when it comes to Jtag, we need to get something called a Jtag adapter. We can either buy them commercially. There's proprietary ones like the J-Link one from Seger. It's got some features that I like. It's got some features that I don't like. But that's the way it is. And then there's a completely open source one done by Dangerous Prototypes called the Bus Blaster that I really like. I don't actually own one because I wound up buying a fly swatter before I had done my research. Okay, and in order to do all that, we need to get our tool chain together. Almost everybody uses the GNU compiler tool chain now, and that means you use GDB for your debugger, and GDB can talk to these Jtag adapters and allow you to debug. It's really quite nice. And that's kind of my wrap up here. I will say that if you want to have your own surface mountability at home, you should be thinking in terms of at least $100 expense. It may get as high as, you know, $300–400, depending upon what quality of tools you get. You can spend $400 to get a really good soldering iron, okay, and I know people who have done that. So that's kind of where we're at. And I guess I just want to leave people with the realization that, yes, surface mount is something that you can do, okay? It's a little nervous at first, but yes, it's very doable, and you just want people to show you how to get started so that you can do it, and then you'll be doing it like the rest of us. Okay. So we'll push the red button. Sayonara again.